All right, let's get started. Welcome, everyone. Hope you're all staying safe and healthy. Um, my name is Surya. I'm a machine learning engineer here at Eliiza. So I'm going to talk to you about how to productionize ML models, especially the ones developed in R. Um, Before we get started, let's get some housekeeping stuff out of the way. If you're new to our brown bags, we ask you to please stay on mute and turn your video off so that the bandwidth is so that the load on everyone's bandwidth is easy. And also, we do give ample amount of time towards the end of the brown bag for Q&A, and we try to make it as interactive as possible. Please submit your questions to the chat feature in the Hangouts meeting, and also all our brown bags are recorded and published to our Eliiza YouTube channel. You can find the link when you get access to the slides here. And also more MLOps, productionization, and data science brown bags are coming. So stay tuned. You can do that by signing up to our mailing list here. And working with us. So if you're keen on exploring some of the ideas further on how to optimize ML models in production or enhance your data science practices and tooling, we can help. And also if you want us to host something specific for you and your team, it might be a brown bag training or something else, we can help to you. You can directly reach out to us at info@eliiza.com.au. And also, so I'll be doing a live demo, and then the slides are available at this link as well on my GitHub, and I'll just post that link in the chat so that people would have access to it. I should have copied it instead of trying to type it. There you go. Hopefully that's the right one. And if you want to chat to me further on some of the stuff that we have discussed, you can reach out to me on my email or on my LinkedIn. All right, now that these things are out of the way, let's get started. So the reason for me to do this talk is that, like if you look at machine learning or data science, there seem to be a plethora of resources that are focused on developing, training, and building ML models. Not so many on how to let other people use them. That's especially true when it comes to R. And I have seen that. I have seen large people, data scientists in large enterprises, also struggle to large enterprises with established DevOps practices also struggle to put their models to production. Sometimes, if you look at DevOps engineers and data scientists speaking, sometimes it seems like as if they're speaking two different languages, and in a sense they are, because productionizing ML models or anything related to machine learning is not as straightforward as productionizing stuff in software engineering. Not to say that it's easy in software engineering world, but we as data scientists or ML practitioners have to deal with another additional access of data as well that makes things complicated. And also we work on a very iterative process here that makes things complicated as well. So in other words, there are more moving parts in ML or data science. So usually to bridge this gap between DevOps engineers or software engineers and data scientists, people like me, machine learning engineers, are dives into a couple of the approaches, and also we'll take a look at the deployment options that we have on public cloud, and then compare them, and also briefly touch on operationalizing deployments. And so all this stuff, even though they're targeted at our users and people who love R, they are valid to other languages. So these ideas and practices that I'm going to talk about are language agnostic, right? So let's. I'm going to put forward a statement. Hopefully, that's not very controversial here. So I'm going to say that if you have if you have two models, one is a state-of-the-art model, which has like 99.9% accuracy on your data, and also a very simple model which has about 80% accuracy on your model. So can you imagine a scenario where that model with lower accuracy is more valuable than the state-of-the-art model? I think I can. It's more valuable when it's put in when it's actually deployed. So if we look at the slides here, this is what Morphy is saying as well. So the best model that you have is the one that's deployed, not the one that's sitting on somebody's laptop or on the cloud. Hopefully that's not too controversial. So let's take a look at the general ML lifecycle. Generally, in a typical machine learning solution, or typically in solving a machine learning problem, we would initially start by defining the business use case for the problem, and then we'd do a little bit of data exploration. Then we try to experiment with a bunch of models, algorithms, and then do a little bit of feature engineering, build a minimum viable model which does all right on the data set. We test it, and then we present those results, and then once things look promising, we'd train that on the larger data set. We'll plan for deployment, and then we'd actually deploy that in an environment, and then we try to operationalize it and then monitor it afterwards. So this particular talk, we are looking at that green. We're primarily looking at this green area where we look at planning for deployment and also operationalizing, and touch a little bit of monitoring as well. So those of you who are wondering what the heck is productionizing, it's a made-up word, obviously, and then I would define it something like this. It's a verb, and then it's the process of taking a developed model, finalizing it, and making it available and ready in an operationally active and production environment. So there are two aspects to it. So one is making it available and ready. That's a one-off thing, but at the same time, there is another aspect to it where we want to make sure it's in an operationally active environment, and that we are able to operationalize the deployments in the future. How would you use this made-up word? You could go to your boss and say, "Hey, boss, watch out for the extra revenue. I've just productionized my model." So if you're wondering how, then this is one approach you could take. I assume most our users are familiar with something like this, where you would try to wrap you try to wrap your machine learning model, and then the inference code, the code that's used to extract predictions out of the ML model, in a backend, put an UI in front of it, and then deploy it somewhere. Those are, if you look at Shiny or R Markdown, that's what they're doing. So the approach they take is deploying ML models as a standalone application in front of the user with an end user facing UI. But it's often the case in the industry that you don't deploy all your machine learning models in user facing UIs. Often your company would have your website, or your company would have their own UI, and then you'd want to integrate your ML models with other services across your company. So often what we would look at is we would be working in a microservice architecture world where you would want to deploy your ML model as a microservice that's accessible by other microservices in your organization to get predictions out of the model. So we would be focusing on this sort of ML microservice architecture for the rest of this talk, where so if you look at the core idea, it's very simple. So like most of the data scientists or people who are working on developing ML models are would be familiar with the concept of inference code. That essentially is the code where we would load the model, get the data that the client is requesting, and then get the predictions out of it, and then send it somewhere. So so in the idea of it is the core idea of a model server is that we would wrap the inference code and the ML model in an API, and we'll deploy that API on a server, and then this server would take incoming prediction requests from the clients. These clients might be other microservices in your organization, or could be end users if you're exposing this API publicly as well. And then the server would take the incoming prediction requests, sends it to the inference code, which would get the predictions out of the ML model, and then those predictions are sent back. So if we do something like this on a bare metal compute instance, we might run into something like this at the end, where we would run into a dependency hell. Even though this diagram is looking at Python's dependency hell, rest assured there are dependency hells in any programming language where there are more than one moving parts. And we would run into the classic scenario of this has worked on my machine, but why hasn't it worked on yours? So the solution for that is something called Docker. So for those of you who haven't heard of what a Docker is, it's essentially, you could think of it as a package where we package up everything that's required for our software application to run into a container, and then it would everything that needed for our application is packaged up into this container, and then we would deploy that somewhere, and then it would run without having to depend on other stuff, other external dependencies. So if by slapping in a Docker container on top of your server, this HTTP server here, which serves the API, we are encapsulating the dependencies that are required for either our inference code or for our API for our entire software application. And also, it's easy to deploy a Docker container on various operating systems, and then this can be done in a repeatable and a scalable fashion. So if you're looking at the scale, you could essentially deploy a Docker container on a container orchestration system like Kubernetes or other cloud platforms, and then run as many containers as you would like to scale your application up to meet the user demand. So yeah, at scale, we'll be deploying Docker containers on a Kubernetes or cloud managed platforms. This could help us with deploying. This could help us in doing complex deployment scenarios, wherein sometimes we would often want to have multiple models in production to analyze, to sort of do A/B testing on which models are performing well against the real data, and also if these Kubernetes or these cloud managed platforms are often are used often use computational resources more efficiently, and then they're hardware agnostic. As long as it's a Kubernetes cluster, it doesn't really matter where it's running, whether it's running on a set of Raspberry Pis or whether it's running on a bunch of supercomputers. It doesn't matter. The deployment process and the way you interact with it is exactly the same. And then they often come with auto I'm looking at this particular Docker image that somebody else has built, which is Rocker ML. Rocker project is a cool project. I recommend all of you to check it out, where they install these Docker ML image comes pre-installed with bunch of things that we need for us, like our RStudio, TensorFlow, Tidyverse, etc. And then Docker distributes a few other images as well, depending on the need. I recommend you to check it out. So in this file, I'm essentially what I'm doing is I'm copying my relevant files, app.r, plumber. Like we did in our example, and also there is this other problem where where, let's say, our for some reason our inference code breaks, and then that would essentially take down our API and then the server as well, the HTTP server as well. So there isn't much visibility upstream for the processes if you're not careful. So it's always advisable to have have health checks in place to check that things are working and readily available for us to send prediction requests. And also, it's recommended that we do auto restarts on when we deploy these containers. It's recommended that we configure them with auto restarts, so that even if a process or a container fails, we would restart it again, and hopefully that staleness that led to the breakage uh, would not be there when we are restarting it freshly again. And another pitfall is if you're using these pre-built images, they can get bloated. So the start times of them of these Docker containers might be really high. So for example, this Rocker ML image that I'm using is about 7 gigabytes because they have installed a bunch of stuff while trying to appeal to a wider range of audience. So it's always recommended to build your own. It's good to these pre-built images are easier when for experimentation and prototyping, but when you're productionizing stuff, it's recommended that we keep these containers as lightweight as possible. So by building our own images, we would only include hopefully we would only include the stuff that is essential for our deployment. And also this can be computationally inefficient because R is a single threaded language, and in any Docker container, we only have one R process running. So for example, a Docker container can only process one request at a time. So so when we are deploying it, we need to make sure we need to keep that in mind. So for example, if for some reason my prediction request is taking couple of seconds and other prediction requests come through, they would have to wait until I process my first one. So it's advisable to deploy multiple lightweight replicas of the same container with an external load balancer that would forward the traffic to the ones that are available at that point. Some of you might think there is another approach where we could start multiple R processes inside the container itself, so that and slap in load balancer within the container. That again is not recommended in my opinion, because we would be unnecessarily bloating the Docker containers. So a general rule of thumb would be to keep them as lightweight as possible. And so to avoid to sort of so the like if you're building model servers in this fashion, these pitfalls are very common. So people out there in the industry have built open source tools which try to avoid these pitfalls. So let's say if we are leveling up our leveling up our model server, we'll be using an out-of-the-box tools, a tool like TensorFlow Serving. So what is TensorFlow Serving? It essentially, if you look at the image here, it essentially encapsulates the API server and then the Docker that we had in our DIY solution. So TensorFlow, as most of you would be familiar, it's an open source machine learning library. And then recently, I think a couple of years back, they have open sourced TensorFlow Extended, which is which are a bunch of tools that aim to make people's life easier when people are putting machine learning models in production. So if you look at TensorFlow, TensorFlow Serving is one such tool. So it's off the shelf, so we could readily use it by giving it only our model file. But there's a caveat here where these models, there's only the out-of-the-box support is only for models exported by TensorFlow. So the reason being, when a model is exported, when we are serializing a model by, say, save RDS, we are only serializing the model file, but not the computational graph to it. But when TensorFlow, when it exports a model, it essentially saves the computational graph also. So we don't need to give it an additional inference code for TensorFlow to make predictions on our model, because that computational graph is saved within the model itself when it's exported by TensorFlow. So yeah, TensorFlow serving offers consistent APIs. They offer gRPC APIs and REST APIs also. And by this approach, we are essentially separating API code and our models. And also, it comes with out-of-the-box support for health checks, model versioning, batching, and it also supports complex deployment scenarios with multiple model versions and all the fancy stuff like that. So how does TensorFlow serving look like? It's pretty simple. If you're using a TensorFlow models. So as a TensorFlow, they supply these Docker images for TensorFlow serving, which is this one, TensorFlow/serving. So I could essentially start serving my model by running this Docker image with a bunch of config in there, where the key things there are the only key thing there is this part where I am essentially mounting my model, which is in my local system, onto the Docker container. So that's where I'm giving the TensorFlow serving my model. And then we could, as soon as we run the Docker image for TensorFlow serving, we could start sending prediction requests to it by using this tool called curl, which is a command line utility on Unix systems, where we could send HTTP requests with the inference data. So let's see how these things would look in action. So let's do a live demo on these two approaches and how things would be. So I have like I've shared my repo here for the demo. If you take a look at it, I have a train.r file where I have essentially trained two models in here. This is all R code. I've trained an MNIST model using TensorFlow on the MNIST data, and then also I've trained a random forest model on the iris data. I'm sure most of you are familiar with those two data sets as toy models for this demo. And if you look at the other files here, they're essentially what we have discussed. So I have my predict.r file that I have showed, which has get predictions and load model functions, like we have discussed. And also I have my plumber where I'm defining those two routes, ping and invocations. And also I have my server, HTTP server plumber file, where I'm processing the API and starting the server. And if you look at the Docker file, it looks very similar to what I've discussed, with one additional step. Let's not worry about that. It's a multi-target Docker, multi-stage Docker container. So, but if you look at this part, it looks exactly the same as what we have discussed. And so I have that here in my. So I've cloned that repo onto my machine here, and then I'm sending these commands using something called make. Let's not worry about it. So for example, let's say I want to deploy my Iris model with a DIY solution with Plumber and Docker. I would just run this make command called make deploy Iris Plumber that I have done. And if we let's not worry about the make file, but at the same time, I'll just show you what this thing is doing. It essentially is running these two commands where I'm building the Docker image and then I'm running it. So if you look at, so that thing is done. So if you look at the Docker containers that are running at the moment, I have my Iris Plumber Docker container that's running, that just started by my command here, and I want to send prediction request to it. So I have the data for that here. So I'm sending it 4 data points for Iris. Uh, 4 data points in the Iris data set, which have these features for each of them. And then the model is trying to predict which species of Iris thingy is that. So let me send a prediction request to it by essentially doing a curl in there. So as you could see, I've done a curl and then I've given it this data I've hit my URL there that's deployed locally. So as you could see, my model has predicted and written the predictions. And in this particular case, all of them are setosas. So that's the DIY solution. So let's say we are deploying let's deploy our MNIST model with TensorFlow extended. And again, in the make file, if you look at it, I'm essentially running this command, which is what we have looked at during the presser. And something happened. So that should work. So yeah, it started the container with one easy step. So if you look at the Docker containers that are running, you could see there is a second Docker container that just started now. And so I'll send it, since this is MNIST data, you could see I have 2 instances with essentially pixel MNIST data there. And so let's send that request to my thingy there. So yeah, I'm essentially sending another curl request, but to a different URL, because that's where my TensorFlow is serving my predictions. And as you could see, I've sent 2 instances of MNIST data points, and then I've got 2 prediction requests back. So in this particular case, both of them are 0 digits. So like both of them are 0 character. That's what they're showing there. So all right, so let's get back to our presentation after that quick demo. Feel free to take a look at the code. It's on GitHub, and get back to me if you have any questions in there as well. So all right, so what other options do we have with these model servers? There are, like TensorFlow serving, there are a few other projects which aim to do pretty much what TensorFlow serving is trying to do, which is give out-of-the-box support for out-of-the-box model servers for serving our model predictions. So another project is TorchServe from the PyTorch people, which, yeah, like I said, TorchServe is also very much like TensorFlow serving, where it is language agnostic. So It doesn't matter whether you've developed your model in Python or R in any other language that Torch supports, as long as those models are serialized or archived using the Torch's inbuilt functions. It's able to serve the models. Model servers using those models. Operating system agnostic way. So let's see where we can deploy these Docker containers once we have them. Docker containers or model servers. I'll be using those two words interchangeably. So we could deploy them on, if you look at the major cloud providers, most of them offer something called container as a service. So essentially what this container as service do is we would give these cloud providers a container image, and then they would run it for us without us worrying about the underlying infrastructure or compute. For example, AWS has this thing called Elastic Container Service. Azure has Azure Container Instances, and Google has Google Cloud Run. So essentially, at the end of the day, we're giving them a Docker container, and then they're running it for us. That's an oversimplification of it, but yeah, that's what it is at the end of the day. And we could obviously, if we have a cube cluster in our organization, that's probably the recommended way of deploying these Docker containers or model servers. So on Kubernetes, we could deploy them as a native Kubernetes deployment. That's a Kubernetes deployment is a Kubernetes thing where we would essentially define our application in the deployment package, and then we could expose it as a Kubernetes service to other Kubernetes services in the cluster or to the external world. And there is this other thing called Kubeflow, which is a data science and machine learning platform, which lives on top of a Kubernetes cluster, and it's heavily backed by Google. It's an open source. It's open source now, but it was developed initially by Google. And Kubeflow offers few options with their own serving mechanism called Kubeflow serving. They also allow us to deploy these things using TensorFlow serving on the Kubeflow ecosystem, or Sheldon core serving as well. And on the other end of the things, we have these cloud ML platforms like AWS SageMaker or Azure machine learning platform, where we could essentially give them a Docker container with the inference code by sticking to some of their standards that they have put forward, and then they would deploy that as an endpoint for us as well. So let's take a look at and another option is this platform as a service hybrid, where they're essentially a serverless model a server, and then a compute target as well. So typically these so I'm talking about stuff like Google AI platform or Azure machine learning or AWS SageMaker here, but not the BYO Docker containers, but essentially using deploying stuff on their platforms natively. So yeah, they're typical, like things vary slightly between these three, but they typically have limited support for libraries and models or runtimes, and that support gets even more limited when it comes to R language. They are, in a sense, serverless, as in we don't have to manage the underlying server, or we don't have to worry about installing the right dependencies, as long as we define as long as we pick one of the out of the box configs that they provide us with. And also they're very scalable, as in they could go anywhere between 0 to world domination based on our demand, and they are often pay per use, as in we don't have to pay for them when they are in the 0 state where everything is turned down, and they often charge for the computational resources underneath for the serving, but not for managing those computational resources. They're often pricey if you look at the price. So there is often a price markup for the underlying compute. For example, if you look at SageMaker, we would have to define, we would have to select an instance type. So if you look at a particular instance type in the SageMaker, it's usually a bit more marked up. The price is a bit more marked up compared to a similar EC2 instance, for example. So the typical deployment flow is something like this, where we would have to upload our model to their storage, and then we would have to register a model resource on the platform. This is the custom resource on their platforms, and then we would have to supply an inference code or script, and then define the deployment or endpoint config. This is usually the typical flow in deploying stuff onto these platform as a service ML platforms. And right, so there are a few options here, right? So if you're considering what options to choose for your use case, something like this, a matrix like this could be useful, where here we have 3 deployment options, where the first one is do it ourselves model servers, or out of the box model servers like TensorFlow serving or Torch serving, etc., and platform as a service deployments. So when it comes to our support, with DIY solution, it's available. We can do whatever we want. But when it comes to out of the box servers, as we have seen, they would either have to be usually the R support is limited. Either they are in alpha releases, or there's limited R support. And when it comes to platform as services offerings, it's very limited and often non-existent. And when it comes to library support or the model types, with our DIY model solution, we could virtually use any model or library that we want, and so on. Feel free to take a look at it at your own time. But at the end of the day, we would be choosing a DIY model server for its flexibility. if we want more flexibility in our deployments, and we'll be choosing out-of-the-box model servers. If we'll be choosing platform as service when we need low maintenance or low overhead, and in most other cases, it's better that we choose these out-of-the-box servers. So that's right. So we built a model that's level 1, deployed one model that's level 2. And level 3 would be operationalizing our model deployments. We could do that by doing a few things, and these are some of the things that we could do to operationalize our deployments. Operationalizing, in my mind, I think of it like this: deploying the same thing or similar things in a repeatable fashion by automating as many things in the deployment as possible. I recommend you to use version control for your code, data, and models. These are a few options available. And then I recommend you to test your ML solutions. It's a bit more complex compared to other traditional software solutions. Tim Fist, who is also an ML engineer at Eliiza, has given an excellent brown bag on how to do test-driven ML. I recommend you to check it out. And then often to automate some of the repetitive steps, we'll be doing continuous integration and continuous delivery. And then last but not least, there is an essential step of model monitoring because in production, after we put models in production, because the real world data might differ from the data set that we have trained it on, and a few other things. a.k.a. has given another excellent brown bag on concept drift and model monitoring, which is on our YouTube channel as well. And I've listed tools for each of them right next to it, but at the same time, most of the cloud providers offer custom solutions for each of these steps as well. And another thing is, often in ML we tend to combine a few of these steps together in most ML workflows, and those things are called pipelines. And then I recommend you to check out Shin's and Lucas's brown bag on ML pipelines as well. So at the end of the day, a production machine learning system would have would look something like this, where the ML code is a tiny component compared to everything else that's needed to keep that thing running. This is an excellent paper written by the folks at Google. Take a look at it if you have time as well. And my 2 cents for this talk is, without sounding very anticlimactic, I would recommend you to use Python if you can. I'd say it's a friendly suggestion from a fellow ML practitioner. The reason, these are the reasons, in my opinion, to use Python over R. It's more and more ML and DS libraries or tools are being developed in or for Python. And in my opinion, I've worked in both R and Python world, and then in my opinion, it's easier to find answers in the Python world when we get stuck. And also patterns or practices for accomplishing a task are more standardized in Python world. That's also my opinion. But at the same time, it's a fact that first-class support for Python by cloud providers or open source tools or MS and DS platforms is offered. So, and also Python usually tends to be faster and more efficient than R, computationally speaking, for similar tasks. And these are the references. There are 2 other excellent talks on ML ops, and I've been inspired by them to give this talk. And my demo repo is here, and then docs for the stuff that we have talked about is here. And also there's this cool production workshop in Shiny. That's the stuff we have skipped. You can check it out as well. And I hope you got something out of this brown bag, and thanks for joining us.